I hope the slides are visible to all of you, as well as I'm audible to all of you. Anyone from TA side? Can you please confirm? Hello?
Yes, sir, you are right.
Okay, okay. Just okay, so let us get started. So yesterday, as you know, that we completed our first module, that is on semiconductor electronics. So today we are starting this module 2 on PN junctions. So PN junctions and the PN junction based diodes and all other devices based on this PN junction. And before we go into actual PN junction discussion, so we are yet to have few other general discussion like this related to current and carrier transport, because once again, if I repeat, the overall objective of this course is to understand the current voltage relationship or the current voltage characteristics of typical electronic devices. So in order to understand the current voltage characteristics of PN junction diode or all other devices also, like what are the things we still need to understand, that we will discuss today mainly. So this is the broad outline of this particular module as per the syllabus we have for on this PN junction. And now this is, I think, you all know, like the typical current voltage characteristics of a silicon PN junction diode. So this is the forward biased characteristics. So the when our diode is forward biased, so we have huge or large current flowing through the device. So and when we'll operate our device in the reverse bias direction, so it will not allow any flow of current. So again, if we keep on increasing this bias, so maybe at certain high voltage, very high voltage, so there will be current, but that is called the reverse breakdown, or when you will not be able to control the flow of the current. So that is beyond the control of your beyond the control you can have on your device. So typically, we do not use this breakdown that region anyway. So there are typical other devices, as you know, that Zener diodes are used in the breakdown region. So now, this in this way, the overall, if you just simply look at the current voltage characteristics of a diode, so it says like in one direction it will allow the current, and in another direction it will not allow the current. As simple as that. Like so now, the overall objective, as I just mentioned, how this current or how this blocking capacity is arising in the reverse bias direction, and how this same device structure is allowing current when you are forward biasing the uh, diode. So you know this certain concepts, like you know this there is a depletion region, and that width will decrease, increase. So you know from I think from some top level abstraction point of view. So once again, we'll try to look into details like how this behavior or the current voltage characteristics is appearing in case of normal PN junction diode. So not only this PN junction diode, again you know this for your typical MOSFET, you have this output characteristics. So if we keep on increasing the drain bias, so after some your current or drain current, your current will get saturated. So why this characteristics is coming? So still we need to understand few underlying concepts. So to understand that, so essentially what we'll try to discuss few fundamental semiconductor equations, because once again this is experimental observation, right? Now this using equation, whenever we'll be able to explain these characteristics, this blue color curve, whenever we'll be able to explain this blue color curve or the characteristics using some mathematical equations, that means we understood the underlying phenomena. So what are the fundamental semiconductor equations we need to deal with when explaining this all current voltage characteristics of semiconductor device? So perhaps this class is very important considering this particular objective for this EE311. So if we write like any current voltage characteristics, so this current voltage, or let's say IV characteristics. So this IV characteristics is typically is, as we understood previously in previous class, that this current density J essentially in semiconductor is the current density due to your electrons as well as holes. Now this current density also, so this is somewhat I am trying to recapitulate the previous class. So then we'll see what are the fundamental mechanism. So this, you know, this electron current density is actually, you can write in terms of drift current plus diffusion current, and similarly your whole current density you can write here, as you know, you will have negative because this is whole. So this is the two fundamental equation we have seen just from our previous discussion or the last module discussion. So this is the drift part and then the diffusion part, similarly for your holes also. So to calculate your current or the IV characteristics, so essentially we need these three parameters. So what is psi? Psi is the potential or the bias we are applying. So minus d psi dx is actually your electric field. So if we understand these three parameters, so we'll be able to calculate this current density individually for your whole electron, and then we'll get the overall current density. So then we can understand this IV characteristics of your devices. In more detail, if we write, so this these three parameters, if we write, so and if we observe these equations, so here I am mentioning this partial derivatives. So if we understood, or if we can calculate, or if we know these parameters, at any instant or throughout our semiconductor. So we will be able to calculate these IV characteristics. So these are the three parameters. If we understand or if we can calculate for each point of our this semiconductor device, so then we eventually get this IV characteristics mathematically. So again, following this, in case of steady state condition, as we know that there are different conditions like steady state, thermal equilibrium. So in steady state condition, so if we just understand this parameter, or if we know this parameter at any point of your device, so then we can calculate this IV characteristic, because in steady state, so all the forces are equally balanced by the opposing forces, like recombination and the generation equal. Then you have the saturation in the current. So that is why, so there is a no spatial distribution or the spatial variation in the electron concentration, hole concentration, or the potential. So then in case of steady state, if we understand or if we know these parameters at any given point, so then overall the device characteristics we can calculate. But if it is not in steady state, we need to calculate or know these parameters at each individual point. So to understand or to get the overall picture or overall characteristics of any device. So now, one second, okay, I should have just following these three parameters. How to calculate these three parameters? So or how to your this understand this three parameter in more detail. So then we need to understand few this equation. So first equation is, actually I should have continued from the previous slide actually. Okay, so I can write here. So we need to understand this Poisson's equation. So what is this Poisson's equation? I quickly write this. So this is the Poisson's equation. So this is P minus M plus into ions, donor ions, acceptor ions. So this is the Poisson's equation. What is the, like, this equation is equation, like, what is the significance of this equation? This equation actually relates potential or the electric field developed within the semiconductor with the charge. So this rho is the charge density or the charge amount of charge you will find in the semiconductor per unit volume. So this rho, how this charge density is related with the potential or the electric field, that you can calculate from this Poisson's equation. And similarly, we have other few equation or the fundamental semiconductor equation, like electron continuity. I can write here electron continuity equation as well as hole continuity equation. We'll once again explain all these equations. So what is this electron continuity equation? So electron continuity equation actually relates your electron concentration with space as well as time. So how the electron carriers are is varying in throughout your device, like in terms of space, the spatial variation of electron within the device, and the time variation of electron within the device, you can understand or you can calculate from this electron continuity equation. So this electron continuity equation in semiconductor, if I write, it has this kind of form. And similarly, the hole continuity equation or the distribution of holes with space as well as time, or the variation of holes with space and time, is, here we have minus Jp minus Rp. So here you can see this is the relationship or the electron concentration, this variation with the time, and this is the current density variation with the space. So this is a space-time actually correlation, and then you have this G is the generation of electron and the R is the recombination of electron. And similarly, this is in case of generation of hole, recombination hole, and this is the hole current density variation with the space, and this is the hole concentration variation with the time. So these are the two continuity equations. And finally, those this Jn and I'll not write this equation, or okay, just for the sake of completion. So those two current density equation. As well as Jp so these are the equation. So if we number, so these are the continuity equation. So 1, 2, 3. So these three equations are actually these are 1, 2, 3, 4, 5 equations. So we need to understand, or we need to formulate these 3 or 5 equations for all the devices to understand the current voltage characteristics of your device. So now you can see to understand or to calculate this equation, so few other constant values that we need to know is for this whole current and electron current density, we need to know the mobility, like electron mobility or hole mobility, as well as the diffusion constant. And similarly, for this, we need to know this generation and the recombination, these parameters, like for holes as well as for electron. And for this, we need to know the doping level. So what is Nd and what is Na. So these are the values we need to know to calculate or to get this equation, this mathematical equation, and eventually we'll be able to get that characteristics of like current voltage relationship or characteristics. So now let us try to discuss like how these equations are coming, like what is the concept behind these equations. I think you know somewhat, like I think that first Poisson's equation, I'm not writing down. So the Poisson's equation actually is, you know, that Gauss law. So the Gauss law says that this is the charge density, volume charge density, or your this unit is once again this coulomb per centimeter cube. And if we write this same Gauss law in terms of electric field, epsilon electric field, then your gradient of electric field, you can write rho by epsilon. Then for one dimensional case, your dE dx will be equals to rho by epsilon. And now, as we know, electric field equals to minus d psi dx, simple electric field relationship with the potential. And finally, you will get that Poisson's equation, which is d2 psi dx2 rho by epsilon. So this Poisson's equation is nothing new, but simply like detailed or simplified version of your Gauss law, or extended version of your Gauss law. So from this Gauss law, once again, it says the relationship between your charge density, the charges in your device, and how the electric field or the potential is related with the charges. And just I think one of you just mentioned in just initial classes, like there is something called Schrodinger's equation. So that Schrodinger's equation, anyway, I'll not go into. I don't know whether this spelling is correct or wrong. So Schrodinger is once again like one of the famous scientists in the last century. So this Schrodinger's equation, from this Schrodinger equation, you can understand the variation, or the where like where you have these charges and how these charges is varying within the semiconductor device. So those who are from engineering physics, perhaps if I remember, you have another course like solid state physics. There will understand more detail of this Schrodinger's equation, or this other concept. So for anyway, for just as a scope of this course, I'll not go into the Schrodinger, but eventually this Schrodinger will give us this rho, or the charge density, or the variation of charge within the device, and this charge density will finally give us the electric field or the potential. Now try to like overall get this picture, like how, because in device, like, or in our objective in this particular course is to understand the terminal characteristics or the current voltage characteristics. Now this current voltage characteristics is all like that means the electric field or the voltage, and how it is related with the charges here. So that we'll get from this Poisson's equation. And then if we go into detail, then you need to take help of the Schrodinger's equation to calculate these charge densities. So now following that, we have other two equations to understand this terminal characteristics. So they are the continuity equation. So continuity equation, and okay, just I need to complete this Schrodinger's equation. So now if we see this semiconductor, any semiconductor bar, so we'll see what are the different charges we'll encounter. So we may have this donor ions, we may have electrons, we may have holes, as well as we may have acceptor ions. Again, we may have electrons or holes. Now in this place of rho, we can simply write, so rho equals to, in case of semiconductor, Q times P. P is the positive charge hole, and here you have ion, that is a donor. After donating electron, these ions are becoming positively charged portion. Then we have negative electron and negatively charged acceptor ions. So in A minus. So now if we plug this row here in this equation, then you will get all the relationship between your charge density and the electric field or the potential developed within the semiconductor. So now let us discuss continuity equation. So this continuity equation, once again, if we write, this is Tx plus, in case of electron, this is the equation, and this continuity equation actually coming from the law of conservation of particle conservation, like particle may be either electron or the hole. So this particle conservation in terms of time as well as the space. So this is like in generic word we can mention particle conservation. And now let us consider one section of semiconductor which has area A. So this area is perpendicular to this plane of let's say our skin, and then we have variation of x, or the spatial variation from x to x plus del x, and this is here we have electron concentration variation with the space or with the x. Now what is the total number of charges or total number of electron within this portion of semiconductor? Simply, so as I mentioned, this is the particle conservation equation. Continuity equation is nothing but the particle conservation equation. So now the total number of electrons within this semiconductor, simply the this is the density, electron density per centimeter cube. So then we need to multiply it with the area as well as the this distance del x. So this is the total number of electrons available within this confined space, or within this semiconductor we are considering. So now what are the factors, or what are the different processes that can alter this total number of electrons within this portion of semiconductor? Once again, I am repeating, what are the different processes that till now we understood or we have seen in our previous module also, that can alter this n, or the number of electrons? So the first one that can lead to this change in this total number of electrons within this portion of semiconductor is obviously electron current. That means, let's say, if we have current entering, which is, let's say, INX, and the current going out, let's say, INX plus del x. So due to this electron current, this is IN current due to electron. So this total number of in, it can change, or the total number of electron, it can change due to the electron current. So how we can write this? So now the total change in the electron, or the total number of electron change here due to the electron current. Let me write this electron current. So this is the process due to which our total electron concentration within this semiconductor is changing. So this is electron current. So this del N will be del Nx, that means the electron concentration change with area multiplied. So this is the electron current. This change is due to the electron current, or due to the difference or the variation in the electron current. So it is del X, which we can simplify further as in terms of current. Now we need to understand this, or we'll write this del Nx in terms of current. So in terms of current, if we write, this is the electronic charge I in X is entering, and I in X plus del X is going out. This is multiplied by delta T. Is this equation understood? Like, because if we say this is the this is the current. Now if we divide it using this Q and multiply using T, so then you will get the total change in the electron concentration. Total change in the electron concentration, that is del N, which is due to the difference in the current. So current going into this terminal and going out from this another terminal, and due to this there will be variation in the total electron concentration del N. So this is the equation, and now we can write or further simplify this. Del N, sorry. So just we are rearranging this previous equation. So del Nx multiplied by area, keep it. Still we have 1 by Q, and now we have In X minus In X plus del X divided by your del X. So this is just, we are simplifying this equation. So this, here we have del N X, and this is the del X. We are taking from here to in the denominator here, and now we have this form. This, now this one we can write finally. So 1 upon Q, and here we have current, and if we divide this current with the area, so if we take this area from here to here, so then what we'll get, that we'll get the current density, and that means the J in X minus J in X del X. So that is the difference or the variation in the current density of going in and going out. So then that thing we can now write, see, and if we consider this going out, this current is higher, so then this negative term will go away. So then we can now write here in terms of current density, del gel in del x plus something. So this is the first this few terms we can see. Now this was the our continuity equation for electron, and now we already got this portion of our equation. Now what is this another factor, because as already we started to discuss, like the process which will alter the total electron here. So one process is the electron current, so electron current going in and going out. So another two process that will alter or that can alter this total current here or in. So they are generation of electron, as well as the third process that can alter this total electron is simply recombination of electron. So now see, now if we just simply here, so due to the generation, there will be variation in the electron concentration of the total electron within that considered portion of our semiconductor. So here we can write this generation, and then the recombination. Whenever there will be recombination, the number of total electron will decrease, so negative Rn. So now we can just simply ignore this portion. So this is the continuity equation for electron, and similarly you can get the continuity equation for hole. And the significance, now the significance of this continuity equation is, see, it is relating your within the semiconductor this how the carrier concentration variation with the time is related with the carrier concentration or the current density variation with the space. So again here this said, okay, so the unit of this generation and recombination is number per centimeter cube per second. So the unit, so then obviously you can understand, like say this is the del nx del t, and nx unit is the number per centimeter cube. This is the concentration per time. So then here also we have this unit as number of generation rate, so number of electron generated per centimeter cube per second. So it also has this recombination has also same unit. So both sides our units are so obviously they are all same. So another significance of this equation or this continuity equation is, see, sometime again I don't know whether we'll be able to cover any that kind of application or not, but let's say you know that your MOSFET or your diode as well as your BJT, we are using them as a switch or as an amplifier. We know that these are the two broad application of our FET. Now whenever we'll use this, let's say our transistor or FET as a switch, so switch means you will turn on and turn off, right? So your MOSFET you will turn on and turn off. So then when turning on and turn off, so then there is something called like just after turning on or just after turning on or turn off. So during the transition, we need to understand how the device is behaving. That means, okay, let me just anyway, I think we'll see more detail. So, but for the time being, let's say just we are applying this voltage, turning on and turning off. Now our current may not follow our this same wave voltage waveform. So then your current may have this kind of phenomenon. So whenever you are turning off your device, so this is, let's say, on, this is off. When we are turning off our device, the current is exactly not decreasing to zero. So then there is a sum. That means again, this is in x-axis what we have t, or the time variation. So the overall my idea, or like uh, my comment is that here we have this electrical parameter variation with the time. Here this is the voltage and this is the current, and this variation we also need to explain using this semiconductor or this fundamental equation. So how we can explain this kind of behavior or phenomena? So that time, see, this kind of continuity equation we need to use to. So now here this kind of behavior we may have. So this kind of behavior. Again, in PN junction also, like we'll see, like there is some switching time required. Like if, whenever we'll turn off, or let's say our this diode was forward biased. Now we have reverse biased our diode. So it is not that immediately the current will be zero. Like, because in reverse bias our diode will block the current. So immediately it will not happen, so it will take some time. So how to get that time variation of these electrical parameters? That means current, mainly current. So that thing we can calculate using this continuity equation. So at that time, we'll once again need to invoke this concept. So this is the continuity equation, and so I think now we have completed this discussion, and we have already derived this two equation from our previous module discussion. And so now we are ready to explain or move away with the other semiconductor device, and then we'll see this how we can correlate our device characteristics, actual like typical device characteristics like diode behavior or your FET behavior with these equations. So now let us try to explain simple diode. So okay, we have some time. So this PN junction diode structure, just okay, I think okay. So here we have one semiconductor silicon chip. Then we have this metallization from bottom side, and we have another this semicon like metallization from the top side, and then we have this glass tube encapsulation. So if we write, let's say this is glass tube. So this is the actually what is inside the PN junction diode, what you have perhaps seen, like at least fourth year student, you may have seen this diode in the laboratory. So that black color, this component. So here inside this we have this silicon chip, and here we have this metal component, metal connection, because obviously we need to connect this any semiconductor with the metal to connect to circuit. So these are the metal, and in between we have this silicon, and surrounding this we have this glass tube. Now if we enlarge this silicon portion, only the silicon portion, what is there? So this is just structural information I am giving. Now I am not giving any conceptual as such information. So how does it look like, this PN junction diode inside that encapsulation? So now if we look into this silicon portion only, or the semiconductor portion, so we have, so this is some typical diode, uh, PN junction diode. So here we have in plus section. The why this is in plus, because the doping level is of the order of 10 to the power 19 per centimeter cube. And then we have this metal, and then we have in here. So this is in, and here we have this P or P plus. So P plus means once again the doping level of the order of 10 to the power 18 or 19, and in N here our doping level is of the order of 10 to the power 16. So you can understand like 10 to the power 16, here 19, once again here 19 or 18. So that is why this is P plus. And typically as a P dopant, boron is used, and here arsenic or antimony, you know, these are group 5 material, and here boron is used. And the thickness, you should like just for your information I am giving, like you should have some idea like what is the actual diode dimension and all other parameters. So this thickness is of the order of I think 100 micrometer, and here this is of the order of 7 micrometer again. This my figure is not in scale, so this is very small portion, and the thickness of this P section is 1 micrometer. So this is the overall your um, semiconductor portion, which is actually this section. So this is the silicon section. So if we enlarge, you will see this kind of structure as a PN junction inside the PN junction diode. So now if we see this uh, semiconductor portion or the silicon portion from the top, you will see something like this. You can easily guess, I guess. So this is the side view, and from top you will see here we have rounded. So these corners are actually rounded. So anyway, so again the typical dimension of this one is from top. This is the top view, and this is the side view. So this dimension is of the order of 1 millimeter, and this is the metal portion. So this is your diode structure, and anyway, so I'll not explain how. Okay, maybe that is a part of your last module. So how we are building or fabricating this diode. So there are few process involved. So you will buy the simple that wafer. If you remember, I showed that in the first few lectures, I think. So that silicon you will deposit. So you will take in plus type silicon, that silicon wafer. So it comes in a rounded like city kind of shape or look it has. So it has this so N plus or 10 to the power 19 doping concentration. Then you will deposit this n-type layer epitaxially on this wafer. Epitaxially means like simply the atomic arrangement of this semiconductor portion will be similar to the atomic arrangement of this wafer portion. So that is why it is called epitaxial deposition. So any deposition is not epitaxial. Epi means above, taxi means in an ordered manner. So the crystal structure here will be similar to the crystal structure here. So after depositing this n-type silicon, so then we are actually implanting this boron atoms. Implanting means like high energy boron atoms are being bombarded here. So then it converts into the p-type, and here we have some masked portion. So typically silicon dioxide is used for the masking. So then only this portion is exposed to the high energy boron atoms, and then it will get converted to your P plus region. So in this way we are getting this PN junction. And so obviously there are a certain reason why this is a P plus, why this is N plus. We'll discuss in coming classes. So why this is not simple PN junction, what we have just simply discussed, or in theory what we have discussed. So in reality this kind of structure is there inside a diode. So now I think before going into this actual now fundamentally our objective is to understand that diode characteristics that just we have seen or we know. So this forward bias and reverse bias characteristics using the help of those five or three fundamental semiconductor equation. So how this characteristics is coming from this diode, that we'll try to understand. So for analysis, so the for the analysis of your this characteristics, we need to simplify, or you need to assume few condition. So it will help us to simplify our analysis. So for analysis of characteristics, our assumptions are, see, the first assumption is okay, the resistance coming from this metal semiconductor here and the metal semiconductor here. See, here we will have one resistive component. So that resistive component will not consider. Okay. So that resistance between your metal semiconductor junction will ignore resistance from metal semiconductor junction neglected. Second assumption we need to consider. So whatever the calculation or analysis we'll do, it is for the one dimension. So we'll only consider the flow of current in one dimensionally. So we'll not consider current flow or the carrier flow in two dimension or the three dimension. So the analysis that we'll do for one dimensional approximation, this is also called one dimensional approximation or one dimensional current flow. Dimensional current flow. And also we'll ignore the resistive component coming from this metal inside. So the metal that connecting metal, it may also give some resistance. So that also will not include, because see why we are I am mentioning all this, because see this resistive component may be a factor deciding the overall slope of this, because you know this is the voltage and current characteristics. The slope will be decided by the resistance of the device. So that if you keep on including this additional resistive component, then the things will be different. So that is why, like, for the just for the simplification, we are ignoring those resistive component. And this is one thing. Another thing, I think, okay, maybe I can use different color. So there is something called diffusion length. So what is this diffusion length? I think okay. So diffusion length is, one second, we'll discuss, but just for the time being. So in the last class we have mentioned this. There is a after generation of carriers, like the if we remember that there was a minority carrier concentration, like when we discussed that direct recombination. So there we have this diffusion length concept. So the length it will travel when before recombining. So that tau p. So then LP, LT, LN. So these are the concepts. So these are the diffusion length. So this diffusion length here, for this analysis, we are assuming that the length of your electron diffusion length is very smaller than the Wn, or the, we can say that this is the total Wn. And another thing, this, okay, I think in this, okay, for here we can draw it here, only that p-n junction portion. So because that is the actual device, so here let's say p, this is the n, and this is the wn. Remember, this is the p region, because here we'll have this electron as magnetic carrier here, and then electron will start recombining, so that wn is here. And here we have this wp, and this one is very greater than diffusion length of hole. This is very greater than diffusion length of electron. And the doping profile means the concentration variation. So it will vary something like this. So if you have any question, please let me know. So this is, this is the simple carrier concentration profile. So this is the n type semiconductor, so, or this only n type. So here the doping concentration of the order of 10 to the power 16, but this is a p plus, so it is of the order of 10 to the power 19 or 18. So that is why, so this kind of doping concentration profile will have. So this is the actual doping concentration profile. So here this is the doping concentration, like doping, and this is the log scale, and this is how this doping concentration is varying. Again, remember, for our actual, okay, actual calculation, we'll consider this is as abrupt junction. Abrupt means our pn junction, we will consider it is having some abrupt, or this p and n portion is meeting abruptly. That means the concentration is as such, like it is changing something like this, but in reality it has this kind of gradient. So but for our simplification, or for this calculation, we'll consider our carrier concentration having this abrupt change. So these are the condition we need to consider for the analysis of our p-n junction diode. So I'm stopping here. I will not move further. So next class we'll start this derivation. Now please let me know if you have any question or any doubts. Okay, if there is no more question, you can leave, and all the materials related to your module 1, that is on semiconductor electronics, I already uploaded in the Moodle, so please check those. And again, if you have any doubts regarding module 1, please let me know further. Okay, so thank you.